We can represent the values of P and G over each of the pixels in a table. Here, each row of the table is a cell location along with their corresponding prediction value and ground truth value. For instance, I4 here corresponds to this cell over here, which specifies that the probability output was 0.8 and the ground truth was 0. Representing P and G in this table will allow us to more clearly understand the loss function. We'll use the soft dice loss to optimize the segmentation model. The soft dice loss is a popular loss function for segmentation models. The advantage of the soft dice loss is that it works well in the presence of imbalanced data. This is especially important in our task of brain tumor segmentation, when a very small fraction of the brain will be tumor regions. Let's look at the soft dice loss. The soft dice loss will measure the error between our prediction map P and our ground truth map G. This part of the loss over here measures the overlap between the predictions and the ground truth, and we want this fraction to be large. Here, when G over here is equal to 1, then we want P to be close to 1, so that this numerator term is large. We also want the denominator to be small, so when G equals 0, we want P to be close to 0. Otherwise, this term would be large and the denominator would be large. Now we take 1 minus this fraction such that a higher loss corresponds to a small overlap and a low loss corresponds to a high overlap. With this intuition, let's now compute the loss for this particular example. To compute the numerator of the loss for this example, we multiply P and G element-wise to get PIGI. For instance, 0.9 times 1 gives us 0.9, so that's entered here. To compute the denominator, we need the sum of squares of Pi and the sum of squares of Gi. Similarly, we can compute these by squaring the P column to get Pi squared and G column to get Gi squared. We can then sum up these columns to get the sum over all of the pixels. We can plug in these values into the soft dice loss for this particular example as 1 minus 2 times 2.2 divided by 2.47 plus 3, which is 1 minus 4.4 over 5.47, and this comes out to approximately 0.2, which is the loss with this particular prediction and with this particular ground truth for this example. The model optimizes this loss function to get better and better segmentations. This completes all of the pieces we need to be able to train our brain tumor segmentation model. We'll look at the evaluation of the segmentation model next.